And so the standard candle is something that will apply as we go along. This is another one that we can use, which is to do with variable stars. So here I have, if you look closely at this, you'll see that there are stars that are changing brightness. So, and they will change brightness at different rates. This is actually a cluster. So you can use this, if you've got a cluster of a few thousand or 100,000 stars, then you're going to have a few variable stars. And so you can also use this method to check that your main sequence fitting works. Okay, so what is this method? Well, it's called the period luminosity relation. And basically, this was Henrietta Swan Leavitt, who was one of the famous Harvard computers the women hired to work through data on stars. And she basically figured out that for stars that we knew the distance to, that there was a relationship between the period of pulsation, that is how long it takes to go from bright to faint to bright again, and how bright it really is. So we've got a bunch of these. We know how far away they are because we've got them with stellar parallax, and then we're watching them going bright and faint and bright again, and then we plot it and we say, okay, if I've got a pulsation period of 5 days, it's got a luminosity of 1,000. If it's got a pulsation period of 20 days, then it's more like 50,000, and so on. And so we've got this slope here that you can see. There's a really nice relationship. And basically what it tells you is that for a Cepheid variable, if you can measure the period, how long does it take to go from bright to faint to bright again, then you know how bright it really is. If you know how bright it really is, then you can work out how far away it is. And it's a standard candle again. And like I say, you can use this to measure the distance to a cluster, so you can make sure that your cluster main sequence fitting is also giving you the same answer. The other thing is that this is in solar units, so we're talking about things that are over 100 times the brightness of the sun and up to 10,000 times the brightness of the sun. And that means that instead of only being able to see out to distances of a few light years, we can now, a few parsecs, a few hundred parsecs, we can now see out to a few tens of million parsecs. So we're able to use this to measure out to large distances. Okay, so now we can measure the distances. Here I've got 1 million parsecs. Okay, so anything that is within this distance, so basically within our local group of galaxies. Here I have the Milky Way, and then we have all these little galaxies that orbit the Milky Way, large and small Magellanic Cloud, Sagittarius Dwarf, and so on. They're all small galaxies that orbit our own. Here's Andromeda, M31, and all these small galaxies that orbit Andromeda. And all of these galaxies are things that we can measure the distance to using the Cepheid variables. And we can see those Cepheid variables at these distances because they are bright enough to be able to see at a megaparsec. And that brings us to the next standard candle. And the next standard candle is the supernova. So here I have a picture. This is a galaxy, and this is a supernova. And when the supernova goes off, and only for a short period, but when the supernova goes off, it is as bright as a whole galaxy, which means you can see it from a really long distance, which makes it a really useful standard candle. Okay, so what's good about supernovae? Well, it turns out that there are enough galaxies that we can measure the distance to with Cepheids or main sequence fitting, that we can we actually have a decent sample of supernovae that we know the distance to. Supernovae are not that common, but there are enough galaxies that we can measure the distance to, and then they happen in that galaxy, so we know how far away they are. And that means we know how bright they are. And it turns out that there is a strong relationship between their light curve and their absolute brightness. What I mean by the light curve is, you can see here, this is actually one supernova looked at in different bands. So this is U band, B band, V band, R band, and I band. And this object, you can see even in these different bands, it's looking quite different. The spots are data, the lines are models trying to understand the data. And you can see how you get a rise in brightness very rapidly. This is usually considered day 0 because that's the peak, and then it drops off. Okay, Now here I have, this is a whole bunch of different supernovae. These are the official names of them from 1991 through to 1999. This isn't all of them, this is a selection. You see how they have different slopes, they have different brightnesses. So this is the absolute brightness. This is in ergs per second, which is like watts, only smaller. It's CGS units because astronomers are annoying. So, we're talking about 10 to the 50 watts up here. And you can see how the shape of the curves are different. And basically there is a strong correlation between the shape of the curve and its absolute brightness. So once we have a supernova, we can watch how its light changes over time. So we can see, it peaks here, and now it's dropping off, and it's dropping off, and it's following this path. Then we know how bright it was at its peak. And if we know that, and we've got the observation of how bright it appeared to be, we can now say, I know how far away it is, because I know how bright it looks, and I know how bright it really is. I want to clarify, there are different types of supernovae. We haven't really covered this yet. This is specifically for type 1a. We'll come back to what the difference between the different types of supernovae are. But this is a summary of what we've just gone through. That basically, you've got supernovae are really, really bright, even compared to Cepheids. And they're more than 100,000 times brighter than the Cepheids. And the Cepheids were already 10,000 times brighter than the Sun. Remember, we have a 1 over r squared dependence, so we can see them 500 times further away. But that means that we can actually see out to about a gigaparsec, which gives us a huge area, but we're reliant on there actually being a supernova for us to see. And so we're able to use this to map out a significant part of the universe and work out how far away galaxies are. Okay. Now, the next one is called the Tully-Fisher relation, and this is about galaxies, and this is basically saying, I'm here, I'm stood watching a galaxy. The galaxy is edge on, and so as it spins around, the side approaching me is going to be blue shifted, because the Doppler effect will blue shift all of those things that are moving towards me. All of this side is moving away from me, so all of this stuff is going to be red shifted, and the stuff in the middle and going across this way won't be shifted at all. And so if you're looking over here, it's going to be blue, in the middle it's going to be unshifted, and on this side it's going to be red shifted. And this allows us to determine how fast the thing is moving. Now, what is it that we're actually going to measure? Because we need to have something that is the galaxy moving and not just individual star motions within the galaxy. And it turns out that there is something we can do in radio waves, which is neutral hydrogen. Most gas is just hydrogen atoms that's completely neutral, it's not ionized. It's cold, so it's not really doing much. And cold neutral hydrogen exhibits an emission line at 21 centimeters. So we can use that to trace out the density of material and also its motion. Now, the question is, why does cold neutral hydrogen give off radio waves? It's actually to do with the structure of atoms and the fact that electrons and protons have spin. So here we have a proton and it's spinning this way, and an electron is spinning this way. It would be in a very slightly lower energy level if this electron flipped upside down. So now it's flipped upside down, so it's spinning the other way. So the proton is still spinning this way, but now this one's spinning the other way. And that makes it very slightly more lower energy. And the electrons will spontaneously do this, and so you get a photon emitted. Actually, one photon doesn't help you, but there's a lot of hydrogen out there, and so we can see the emission from this hydrogen. So what you get is, you've got this spinning disk. As you're looking at it, you're going to have a line width, which is that you're going to have some contribution to the 21 centimeter line here, which is at the rest frame, but you're going to have some that's blue shifted and some that's red shifted, and so what you get is this broadening out. And so if you measure this width, that's actually a measure of how fast this thing is spinning. And then, since we can measure the distance to galaxies using Cepheids, using main sequence fitting, and using supernovae, we can show that this width that you get is actually correlated very well with the absolute luminosity. So what is the total brightness of a galaxy? How wide is this line? And if we plot them again, we get a really nice correlation. Now, the reason behind this has to do with the fact that the more mass you have, the faster you can spin, and the more mass you have, then the brighter you're going to be, because that's what is the mass is what gives you the stars, and the stars is what gives you the luminosity. And so there's a fairly simple understanding of it. But even without an understanding, this is an empirical law that this width is correlated with the absolute brightness. So we have another standard candle. If we can measure this line, and we can measure how wide it is, then we can work out how bright it really is, and then we can work out the distance. Okay, so we've managed to come up with several different ways that are using the previous steps on the ladder to make further and further steps out into the universe, and we're now able to look at, so that local group that we looked at before is just this. And we have these other groups around us, and now using supernovae and the Tully fissure, we can actually measure a huge area of the sky and be able to get distances out to tens of megaparsecs. And so what's next? Well, the next thing has to do with redshift. So here I have some spectra of galaxies, and here you can see this is one that's not moving, and this is one that is moving away from us, and you can see it's redshifted. All of these lines are moved over, and then this one's more redshifted, and this one's even more redshifted, and so on. So what? Well, this is just another view of this. You can see here how the shift relates to the wavelength. Okay, so this brings us to Hubble's law. What Hubble did was he looked at the spectra of various galaxies, actually 5 galaxies for which the distance was already known. So there are the 5 galaxies. He measured the recessional velocity, that is the redshift, and he knows the distance because he's got Cepheids or whatever that's giving him the distance, and finds this really nice trend. And what this says is that there is a simple relationship, a linear relationship, between the distance of a galaxy and its recessional velocity. And as he added more and more objects, he found that this continued to happen. And so he came up with Hubble's law. And Hubble's law is basically just the equation of that line. The recessional velocity is given by a constant times the distance. And that h0 is Hubble's constant. And at the moment it's somewhere around 70 kilometers per second per megaparsec. But what it means is that if you've got the redshift of a galaxy from taking a spectrum, then you know how far away it is. But this particular measure only works for very distant galaxies. And I'll get to that very shortly. Okay, so now we've got that we can use radar ranging within the solar system, and then we've got parallax takes us out to our local area within our galaxy, and then we've got main sequence fitting and Cepheids, which take us out a bit further, and then we've got the Tully fissure and the supernova light curve, which takes us out to 1 billion parsecs. And then we can use all of these to get Hubble's law. And this allows us to measure distances to all sorts of different objects. Turns out then that the hardest thing is to measure distances to things in our own galaxy and that are, not associated with a cluster or whatever, because they're too far away to use parallax, but they don't have enough information. They're not Cepheids, and they're not in a cluster, and so it's actually really hard to measure their distance. And so here we have what is basically a summary of this. So close by we use parallax out to a few hundred parsecs. And then we can use spectroscopic parallax, which is actually kind of similar to the main sequence fitting, which is not mentioned on here, but this is basically the range of main sequence fitting here. So we've got some overlap. We've got these ones get to calibrate this section. Spectroscopic parallax, say that 3 times fast when you're drunk. This is basically using the MKK classification, luminosity classification, where you use a line width to determine whether it's a supergiant or a giant, and then you've got a rough estimate of its brightness, and then you know how far away it is because you can measure you can say this is where it should be on the HR diagram. Okay, so now with the spectroscopic parallax and main sequence fitting, we can now calibrate the Cepheids, And so we've got this overlap here in this 1 to 10 kiloparsec range. And so now we've got these Cepheids, which takes us out to distant galaxies, and those distant galaxies then let us use the Tully fissure and the supernovae, and then we can also get Hubble's law involved. And so this is how we measure distances in space, and this is what we will be doing our term papers on.